Fine?
We are now.
Cool. All right. So, orbital elements, just refreshing what we've done last time. And since you guys told me that you had no idea what order angles were, I'm going to spend some time on them, even though I don't believe you. You should have seen them somewhere, but that's okay. You forget things you don't use. So maybe it was a long time ago. So we said we don't necessarily like every time to use Cartesian coordinates, r, x, y, z, and r dot, x dot, y dot, z dot. You should have all this stuff. I just copied what we did last time. And so we introduce orbital elements where the h is reused, the eccentricity is reused. So my orbital elements or parameters were basically h, norm, the inclination, omega, e, little omega, and theta, for example. So this we knew already how to compute, right? And we actually have defined this at some point, the true anomaly. So those are no news for us, but we're still missing 3 more because we need 6 quantities to tell us where a spacecraft is on a Keplerian orbit. And so we said, okay, why don't we actually define 3 angles that allow us to basically do the following. Take this plane, which is the orbital plane, and tell how it's oriented in the ECI base. And so you really want to imagine this with objects. At least that's the way I imagine this. If you have an elliptical orbit, for example, you can just think about it as an oval, a physical object. Fill it with material if you want. And now you're going to take this and just place it in space, in some configuration. And you don't change it, because for now, the force that we have tells us that h is not going to change and e is not going to change. So once you place it in a certain configuration at a certain orientation in space, it's not going to change. What happens is that your point, the spacecraft, is going to move at the edge of that oval, that's all. But really imagine a physical disk, or an oval disk if you want, that it's placed in this room at a certain orientation. And that is what these 3 angles are going to give me, how that object is oriented, okay? And I'm going to elaborate more on those 3 angles. But we said the procedure now, if I want to compute these orbital parameters that I have, these 6 quantities, is the following. Well, no news here. You compute your angular momentum. Remember, this is per unit mass. We forgot that a long time ago, but this is per unit mass. But that's r crossed with v, so h is done. It's the norm of that. E is this vector. It's the plus vector divided by mu, and that takes care of E. And then all the other angles I have to compute. And I have defined these 3 rotations where the omega, or right ascension of the ascending node, is given by the intersection of the equatorial plane and the plane of the orbit. And I'm going to look at the ascending node and define a line between the origin of ECI and the ascending node, called that line of nodes, n, and the angle between x and n is capital omega, and so that's down here. I'm not going in order here, but that's how you do it. It's the arc cosine of the dot product between n and x. By the way, n comes from this cross product. Correct if the component of n, the unit vector on the y direction, is negative, just do the correction 2 pi minus omega. That's all you need to do. So every time you see correct in this algorithm, if you want to call it that way, that means take the angle you have computed and do 2 pi minus that angle. That's going to be your capital omega in this case. So that's how you compute that. Then, for example, which one do we want to do? Well, should have done this first, probably the inclination. Inclination is defined as the angle between the angular momentum vector that does not change and the z-axis, the north axis, and that's how it's done. And this doesn't need any correction because it's defined between 0 and pi. So the arc cosine, that's exactly what it's going to give me, and that's done. Same story for the other ones. Argument of Perigee. What is that? Is the angle that goes from the line of nodes to the direction of the line of ups, which is the e direction. And so how do I do that angle? Again, I have 2 vectors involved, e and n. You do the dot product between the 2. normalize, because n is a unit vector the way I defined it here, but not e necessarily. So that's how you do it. It needs a correction if the e component in the z direction is negative. So basically your e is pointing south. In that case, you do 2 pi minus d of omega. No big deal. And then true anomaly is the last. That we should really know how to do it, because we have defined it ourselves a long time ago. It's the arc cosine of the dot product of E and R. R is the position of your satellite. So it's this angle between these two vectors, and that's how you do it. And you fix it if you are past the apogee. Now, there are some special cases, as intelligently one of you pointed out last time, where not everything works. And again, I'm going to talk about ordered angles, this particular sequence of ordered angles in a second. But let's first look at these special cases. Some of these vectors, basically, that I'm using here in this algorithm, they just vanish. They don't exist in those special cases. There are two, pretty much. They can also happen at the same time. But those are the two. There are two vectors here of all these number of vectors that I have that can go to 0, or they just cease to exist. The r vector is not one of them, because if this goes to 0, you have a satellite that is sitting at the center of the planet. It's not very useful. So that doesn't go to 0. Angular momentum, can that go to 0? Unless you're shooting an object straight to the planet, in which case the position r vector and velocity r vector are parallel, or you're shooting it straight away from the planet, which it doesn't happen because it's going to be so expensive fuel-wise. H is not going to 0. Impossible. Okay, so don't write h equals 0 in any of the problems I give you, ever, because that means it's not in orbit. It's just going on a straight line, and it's not fun at all to go on a straight line. I mean, maybe an asteroid will hit us that way at some point, but so far we're safe, looks like. But really, there's no orbit in that case. So those cannot go to 0. What else can go to 0? Of course, these are unit vectors of a basis. I'm not going to assume that they can go to 0. What can disappear? Eccentricity can disappear. You can have a perfectly circular orbit, and that's a problem. And as in every sequence for ordered angles, and again, we'll be a little more formal in a few minutes, when you have a sequence of ordered angles, in this case the sequence is omega, big omega, I, little omega. That's how you do it. Again, I'll do it formally. But that will be the sequence. The second angle is always a problem. Doesn't matter what the sequence is. In this case, if the second angle, the inclination, is 0 or pi, we have an issue. Right? What's that issue? It's not a huge deal. We can still survive. We just have to correct a couple of things. But what goes away? This. If you are in the equatorial plane, there's no ascending node or descending node. You're always on that plane. You're not going north or south. You're just there all the time. Doesn't matter what the shape of the orbit is. So n disappears. And so what happens is that you need to make a choice there. And what I have done in the code that I worked on in the last few days, and I'll show you if you have time at the end, and you guys will have to develop yourselves, of course, is that you make a choice. After all, these are all vectors that we are defining ourselves, so I can still come up with an n. So if, say, if the inclination is either 0 degrees or 180, well, you could just say that n is x. There is no real intersection between those planes, but you need to define some direction from which you're going to measure this argument of Perigee at this point, right? So in other words, if you do this, you can just say, the ren is 0. You can. No one tells you that it's forbidden.
Sorry.
Yeah.
Are you saying if inclination is 0
Zero.
or 180,
Yeah.
n is equal, is that?
I choose it. I said, since there is no n, per se, the way I defined it, there is no intersection between two planes that are the same plane. But I still need, because imagine that you have still an eccentric orbit that is in the equatorial plane, right? What that means is that you're going to have something like, what is that, x and y, right? So x and y. And your orbit looks like, I don't know, could look something like this, and the eccentricity vector is right here, right? So now, the goal of the little omega angle there is tell me how that E vector is oriented with respect to the line of nodes. There's no line on nodes here unless I choose a direction. And what I'm suggesting you do, and this is some convention that we agree on, and you could do something else, I'm telling you, okay, you know what, if the inclination is 0, just call this n and start measuring the argument of Perigee from there. It's a perfectly legit thing you can do. Okay? So that's a choice. You could have said, you know, I like this other direction better. So I make the RAN 180. Or I like this better. I make the RAN 270. Up to you. As long as you tell the user which is the direction that you're going to use. Right? It's just a choice. Coordinate systems are always choices. We can do what we want as long as we are consistent with that. But that is not only the only case where things kind of break down. There is another case, as I mentioned, if now E is the 0 vector, it's a perfectly circular orbit. Well, there's no perigee, it's a circle. What do you do? Well, you know what? I'm going to choose the direction of, I don't know how to phrase this, say, well, basically you can say that the line of apse is your initial position, is R or R0. You can do that. Because what do I do with E? I measure the true anomaly starting from E. The direction of E would be fixed in space, and I am going to measure theta as the angle between the position vector and E. But E doesn't exist. I still need to choose some direction from which I'm going to count this angle, so I'm going to choose my R. Right? I can do that. So if you call that the line of apse, then if you have an inclined circular orbit, well, then you still have an omega that you compute. Instead of using E, you use your initial position. These are all choices that, you know, in extreme cases you can make. They're not the only ones, but they're perfectly legit ones. So that this still works. Any questions on this? Yes?
If the inclination is greater than 90, then won't the satellite technically be going the opposite direction of the...
Yes, the ascending node is going to be on the other side.
Okay.
So that's why we want the RAN to be able to go 0 to pi, because it can go past 180 and it can go around. So it's going to cross, yeah, basically instead of crossing south-north here, it's going to happen on the other side. Right?
Won't it be going... What I mean is, won't the spacecraft be orbiting the Earth in the opposite direction as all the other satellites?
Oh!
You said that generally they are.
Generally, okay, so a small correction to that statement. Generally, we don't launch anything opposite to the rotation of Earth because we want to use that initial spin that we have down here already, because we're moving pretty fast. So it's insane not to use that. Except there are some orbits that do require an inclination above 90, right? So if you go above 90, you're rotating the opposite direction of the planet. Those are Sun-Synchronous Orbits. We're not there yet because they use the oblateness of the planet. Basically, you use the effect of the oblateness of the planet so that your orbital plane rotates as fast as the Earth around the Sun, and so your orbit is always illuminated by the Sun. And that is 90, it's a little bit above 90. I think it's 97 something. I don't remember the exact number. It's slightly above 90, and they use one of the perturbations with respect to having a perfectly spherical planet, which is the J2, by the way, the formula I gave you in one of the MATLAB files. So if you put the satellite at the right inclination, the effect is that the RAN actually is going to rotate, but again, we haven't seen that yet, but it's going to rotate, and your satellite is always going to be able to see the Sun, which is great for solar panels, if you can stay in that orbit, yes. So yeah, except that case, which is an expensive satellite to put into orbit, it requires a lot of fuel. You still launch, what happens, you still launch with the Earth, and then you make corrections to the orbital plane. And correcting, we'll see all these things. Correcting the orbital plane is one of the most expensive maneuvers that you can think of in terms of how much thrust and fuel you have to use. But yes, that's a good question. Yeah, it's going to go the other way. So imagine that the Earth is down here, right? And it's going around the south-north axis, right? Any other questions on this before I start with Euler angles a little more formally? So what do you guys know about these Euler angles, other than I'm just giving you 3 angles here, I'm telling you that's a sequence? What do we use them for? You can tell me something. Even if it's wrong, it's okay. This is not a test. So I always, at least that's the way I understand things usually, I go with simple parallels in my mind. So if I have a point in a, and I am sitting in a certain reference frame, call it A, and I have chosen my coordinate system, which is fixed in this reference frame. So there is an origin, there is an X direction, a Y direction, and a Z direction. How do you tell me where that point is? Doesn't matter if it has a mass or not. It's an object, just a point. You tell me X, Y, Z, right? You give me 3 numbers. 1, 2, and 3. How about that? What that means is that you project it in this plane, and then you go with the X, with the Y, and this is the Z, right? 3 numbers. Now, how that point ended up there, we don't know. But I could tell you that in principle, I can imagine this sequence. I can imagine that this point was sitting at the origin, did this, moved on the y-axis, then moved parallel to the x-axis, then went all the way up to z. And I can also do, other sequences. I can do this, and this, and this. They're all going to lead me to that same position, right? That's a sequence. I can imagine that. It doesn't mean that is what has happened, but I could, right? So with that idea, what we do with Euler angles is something similar. We have the reference frame where we're sitting in, again, call that A, with the origin, the directions, etc., etc. And there is another one that is not oriented as A. It's called B, right? It's some X prime, Y prime, Z prime. And always think about reference frames as objects. A is this room, B is this eraser. It's oriented in some weird configuration. You need to give me some parameters, something I can use to tell me what this orientation is. And you can imagine with a point it's pretty easy. Cartesian coordinates, you project a point in a plane, X, Y, Z, it's quite straightforward. You're used to that. Well, here with Euler angles, we try to define some parameters that allow me to tell you 10, 20, 30. Sequence 3 to 1 Euler angles. And you should be able to understand what that is. Because rotations are a little harder than positions. Positions you can commute. I can go to this point imagining that I went through the sequence y-axis, x-axis, z-axis, or x-axis, y-axis, z-axis. They commute, right? I can switch the order. I end up in the same location. Now this object, let's see if I can come up with an example that makes sense. Say that this is the x-axis. I don't know if Patrick can see this on camera. Yeah? Nah. It's an eraser, right? It's a box. X-axis that way, y-axis this way, z is this way. And say that I do a rotation of 90 degrees about the x-axis. And then nothing else. 0, 0. Okay? So now I have a new, the x-axis remain the same. I have a new y-axis and a new z-axis. So I did 90, 0, 0. What if I do 0, 90, 0? 0, 90, 0. Completely different orientation, right? I just took 3 numbers, 2 of them were zeros, and I mixed them up. I changed the order. If you change the order of rotations, they don't commute. You're not going to end up in the same orientation. Again, I was doing X rotation, 90 degrees, nothing else. So the other 2 rotations are 0. If I take the 90 degrees and apply on the y-axis, this is where I end up. So obviously, I cannot do the same that I've done here, right? Do we see the parallel? If you're rotating about axis of this object, the order matters. And you can't just take those 3 numbers and move them around. Okay? So, Euler angles are something we make up to try to represent how this object ended up in some strange orientation in space. And we do it by single axis rotations. In other words, whatever was the orientation that I was trying to represent for B, I imagine that I started from A, so this B object initially has the body axis oriented as A, even if it's not true, even if that's not what happened. But imagine that they are oriented exactly, on top of each other at the beginning, and then to get to the orientation that I'm trying to represent, for that particular sequence that I gave you, I did a rotation about the z-axis with an angle capital omega, and this x becomes some other axis x prime. This is an angle omega. This y becomes some other axis y prime. By the way, x prime, y prime are still in the same plane. And then I do a second rotation about this new x-axis. Imagine that I'm taking an object and I'm doing all this. I take it, rotate about the z-axis, then the new direction of the x-axis, still of the object, I take and I do a rotation about that axis, and so on and so forth. So here this is what I do. I rotate about the x prime axis, and I move z now. Z was corresponding to z prime. And I move z to some other new z, which I call z second. And x prime corresponds to x second. It's not moving. And y prime goes and moves to y second. These are terrible plots to make because sketches to draw because, there's a lot of angles involved. And then, so that was my first rotation about a z-axis, second rotation about an x-axis, and then I'm going to do the last one again about another z-axis, and that is the little omega rotation. So my z third, the axis with the 3 are the last ones, is going to be there. X second ends up somewhere at x third with an angle little omega, and my little y here ends up somewhere with an angle little omega. That's what we have done here using that sequence to basically take this orbit, this oval shape. It was starting pretty much with the E. This is not true. This has not happened, but that's what I imagine to represent this final configuration. I imagine that my orbit was sitting on the equatorial plane with the E vector pointing as x. And then I do a rotation big omega, and my E ends up here. And then I do a rotation about the line of node, and my H ends up here. And then I do another rotation about H, and my E ends up here. And I'm done. I reach my final configuration. It doesn't mean that that's ever happened. It's just something that we create so that we can now give these three angles numbers we can use. In aircraft dynamics, that's what they use all the time. For spacecraft dynamics, if you're going to take classes where they talk about attitude dynamics and control, where things can actually rotate several times about one axis, using other angles is not always a good idea. But for aircraft dynamics, they're used all the time. Roll, pitch, and yaw. They are other angles. It's nothing else. That's what they are. Now, why do we have 12 sequences? Because this one is a 3-1-3. This is what we call it, a 3-1-3 sequence. Because I first rotated about a z-axis, then I rotated about an x-axis, so axis number 3, axis number 1, and then finally another z-axis, axis number 3. So 1 is x, y is 2, and z is 3. So that's why it's called 3-1-3. But there are many other sequences. You can do 3-2-1, you can do 1-2-3, etc., etc. So all the combinations of these three numbers, excluding things of this kind, you cannot do this. You don't want same axes next to each other, because imagine what it would happen. I rotate about this axis, and then I rotate again about this axis, and what's the point? They don't help me at all to represent where that oval is going to be in space. So there are 12 possible combinations of this. Does this bring any memories back? No? Okay, that's fine. But that's how they are defined. So as far as we are concerned, a 3-1-3 sequence is good enough. Now, imagine what happens now when the inclination is 0, the second rotation is 0. Now I forced this approach to still work by saying, okay, I just choose that the line of node, this axis here, is going to exist and it's x. But in reality, that is what is called the singularity. Why? Think about what is happening. You rotate about the initial z-axis and you end up here. Okay? Then what happens if there is no I? Yeah, skip I, right, exactly. So I is 0, nothing is happening. So your z second is going to be here again, and then when you hit this guy, it's going to rotate about the same axis. So basically the first and last rotation are about the same axis. And that is not a good idea. Because that orientation can be a combination of any omega and big omega and little omega. You can find infinite combinations of these that give you the same orientation. Because basically this is what is happening. I'm doing my first rotation about the z-axis. Yes?
What I'm confused about is you said you use big omega, I, and little omega in order for the 313, but you need the h vector to compute big omega, and the h vector is defined by I.
No, h vector is defined by this. H vector exists even if you're not inclined. Right?
You have the angle I before.
Yeah, the I can go to 0. H is pointing like z or the other way. Right? Actually, if you try to do this, if H is all projected on z, you get H over H, which is 1. Arc cosine of 1, for example, is 0 or yeah. So basically the vectors, some can disappear, but again, you do your fixes and the approach still works. But the ones that they're not affected by this representation at all, of course, are the fact that you have a position with respect to the attracting body. Of course, that's not going to go away. You have a certain velocity corresponding h. If you have any eccentricity, that's how you do it. All these other things are just me coming up with angles. You don't have to do that. It's just a choice of representing this motion that the satellite is performing with some other parameters. Now, if you're asking yourself, why the heck are we doing this? Well, because when we start talking about J2, as we did before, Sun-Synchronous Orbits and other types of perturbations, these quantities here, the right ascension of the ascending node, inclination, argument of Perigee, they turn out to be very useful in terms of representing how this orbit is now evolving with time. Because again, if it's a Keplerian orbit, everything sits still there. H doesn't change, E doesn't change. It's just the same orbit over and over again. In reality, that is not true. So you will see that the big omega can change with time, the little omega can change. So the shape of the orbit and its orientation in space evolves, even if it takes days or months, they do evolve. And there are some very nice differential equations that allow us to predict how the motion of the orbit is evolving, and they are based on orbital parameters. It's much easier to see that than doing x, y, z, x dot, y dot, z dot. Because quite frankly, do you see, yeah, x, y, z, x dot, y dot, z dot, but it doesn't give you a feeling of how the orbit is changing. And as long as it's Keplerian, there's nothing else going on, it's not changing. But these angles are going to evolve due to the drag force if you are in low Earth orbit, the J2 perturbation because the planet is not a sphere, the moon, the sun. If you are in geostationary orbits, the moon and the sun, they are a big deal. So there are differential equations that tell you how these are going to change, and it's much easier to visualize a plane that is changing than talking about x, y, z, x dot, y dot, z dot all the time. So that is the singularity there. What I was going to say. I was going to say, so if you have no second rotation, that's 0. Basically, you end up doing first rotation about the z-axis, nothing else, and then another rotation about the z-axis. And that's fine, you know, an object can be oriented this way. But in the end, say that the final orientation is, 45 degrees about the z-axis. How many combinations of, say, little omega plus big omega equals to 45 degrees do you get? As many as you want. 0 and 45, 1 and 44, 2 and 43, etc., etc., etc. And you may be asking yourself, well, what's the big deal? Well, the big deal is that you don't want any representation of your orientation to be not ambiguous, because here you have infinite combinations of these two variables. Well, in this case, I would be 0, right? 0 degrees. But then you have infinite combinations of these two that give you the same physical orientation for the object. Is in the parallel of the XYZ point here, is going back here and telling you that, oh, this point is in position 1, 2, 3, but if you want, we can call that 7, 8, and 9. Or many other numbers. You would never do that, right? That's not very useful. And so that is what happens with other angles. Each sequence has a problem when the second angle, in this case, is 0, when you have a sequence that is called symmetric, meaning that the first and last rotation are about the same type of axis, then the singularity is a second angle 0. If you have an asymmetric rotation like this, it's when the second angle is 90 degrees, and you can do that exercise yourself. Imagine what happens if you do a rotation about the z-axis. Then instead of rotating here, I'm going to rotate about the second intermediate axis, because it's 3, 2, 1, and then about the x final axis. You will see that the 90-degree rotation is a problem, because again, it aligns two of the axes. Okay? So, I don't know if I want to do, because this is basically to give you how to compute the orbital parameters from Cartesian coordinates, pretty much, right? Because that's where we start from. I give you R and V in Cartesian coordinates, and you start doing H, E, etc., etc., etc. And there is the other way around. Maybe we should start doing that. And I have a MATLAB function that does the calculation both ways. And since I didn't have anything better to do, I used the ISS data online to verify that I was converting things correctly, and it does work, believe it or not. So if you go online, actually, on the NASA's website, they give you updates on the position of, for example, the International Space Station, and you will see that they give you Cartesian coordinates and orbital elements. X, Y, Z, X dot, Y dot, Z dot, and then there is a table next to it that gives you what we have computed. I think they give you same major axis instead of H, but that's okay. A, E, inclination, big omega, little omega, through anomaly. So at some point I'm going to give you an uncollected homework to basically develop the function that does Cartesian coordinates to orbital parameters and vice versa. Okay? So let's talk about going the other way now. So what happens if I have the orbital parameters here, and I want to compute R and V? What do you do? Well, what do you think we should do? So I'm giving you these three angles, big omega, little omega, inclination, through anomaly, and I'm giving you the magnitude of E, not the vector, and H, or A. So the given is H, E, I, big omega, little omega, theta. Nothing else. You don't have anything else. This is the state of the spacecraft. With this, you know where it is, because these three angles are giving you the orientation of the orbit in space. Again, that oval, how it's oriented in space. These two are giving you size and shape, H and E. And finally, the theta is giving you where you are on that orbit that repeats itself. Now I want to compute R and V. Which vectors do you think you need to find? Because R and V are two vectors, right? So I am giving you scalars, right? Those are all scalars. 4 angles and H and E. And you need to come up with vectors. So you better start assembling some vectors. Any initial ideas where to start from? True anomaly? What do you want to do with the true anomaly? Which one? Which Cartesian coordinate?
Like R cosine beta is
this x hat, this y hat? No. It's kind of along the same lines, but not those, because r, bless you, if we use the perifocal coordinate system, and perifocal I mean, by perifocal I mean h, e, and the cross product of the two, well, that is what? R, the sine of theta, the direction of the unit vector along E, plus R, sine of theta. Which direction do I have here? Oh, this is an R. This is basically the minus n direction, right? Do you agree with me? I don't have the n and e yet, but yes.
Oh, never mind. I was going to give a suggestion, but I thought you were going to.
Yeah, go ahead.
Do we use, you probably about to explain this, but do we use H, E, and N as our coordinate system?
Yes.
Okay.
H, E, and N is, I think we briefly mentioned this, but really it's just a name. If you choose H, H, N, I'm sorry, E, N, and H, the unit vectors, of course. This is a nice, basis that you can use, and this is going to give you the perifocal coordinate system, right? N or minus n in this case, that's what I'm using. And there was a comment there, yes.
Can you use, if you have your A to B data, can you use that to figure out can you use that to figure out R?
Can I use, I'm sorry, could you repeat the question?
If you have the A to E data, can you use that to figure out
H and E?
Oh, okay.
Yeah, from here, you don't have vectors. Again, this is starting from scalars. That's the problem. They're all scalars. So this is a good comment. If I am able to reassemble these vectors here, then I have everything, pretty much. Because if I'm able to define the direction of the eccentricity in ECI, then I have one of the axes for the perifocal coordinate system, then N and H, the same story. And so do you agree with this one? Can you see what's going on? If you do what we've done for a long time now, look at the orbit from above, from H. R, the vector R, is projecting with the cosine of theta on the direction of E, and it's projecting with the sine of theta in the direction that is it minus n? What ends up being positive?
Doesn't it, wouldn't the sign be negative until you pass apogee?
Yeah. But that theta goes from 0 to 2 pi, right? So yeah, it becomes negative. So is that correct? Is n correct? I'm just confusing you. Is this correct? Is are E and N at 90 degrees? So that is not right. Right? Haha. That is not a good idea. It's almost there, but E and H are at 90 degrees. That's all we know. So that is almost okay, but I can't use N. So we need to use something else. So this is not the perifocal coordinate system. It's almost the perifocal coordinate system. Maybe I can use definitely E. Yeah, right. So basically, say that I use this as the X if you want, and this is the Z. What are you missing? You're missing the third direction. What do you want to do? It's up to you. It's up to you. You define what you want to do. H cross E. Is that okay? Is that okay? E, H, I don't know, right? That's how you do it. I'm terrible with this stuff. You're not sure, just double check. H cross E gives me the second one. Yeah, I like it. That's fine. It works. I did that trick, right? the clockwise arrows. So that's a right-handed coordinate system. That is fine. E and H, I know that they're normal. We did that at the very beginning. So I'm missing the third direction. So how about, I don't know, I want to call this, what do you want to call this? Nothing. I'll just leave it as it is. R, I don't want to make up other symbols here. We'll figure it out. It's H crossed with E. So bottom line, yes, you need to reassemble the main vectors that are characteristic of the orbit, and they're always the same, H and E. You need to start from those. There's no escape. And then you can cross them and find the other direction, as we just did here. And then you can start putting all these things together, because, yes?
Is the second term still negative?
I don't know. H crossed with E, which way is going? So is it plus?
So it's minus n.
No, it's not minus n.
It's like K cross I.
H cross n.
So is it pointing at us more or less, or is it going inside? Okay, so that's a plus.
They're defining a reference frame, so.
Huh? That's a plus. We're doing it together. I can make mistakes. Maybe I do it on purpose, maybe not. You never know. Okay, so we agree that in the end, that is the start point. We need to put those things together. How do I put them together? Well, I need to use Euler angles. I have them. I have the Euler angles. I know how to get to those directions. I need these directions. I know the norm of E. I know the norm of H. But I don't know which way they are actually pointing, and I don't know what time it is, just in case. Yeah, I don't know. But so now we need to really do one rotation at a time with other angles and end up figuring out those directions. That's what I need to do. So I start from X, Y, Z, and I do my first rotation, right? Omega, omega. So Z hat prime is there, X hat prime, Y hat prime is here. This is a rotation big omega. So I'm going to write how the basis, the new intermediate basis, transforms itself, projects itself into the original one, the ECI one, right? This you should have seen somewhere. So I'm going to do this for each single rotation until I can put them all together, and we'll figure out all these axes what they mean. Because some of these X, Y's, and Z's, guess what, are going to be the direction of E, of H, and the cross product of the two. So that's really what we want. Because imagine that these, for some reason, I don't know, the X hat prime, well, not for some reason, that actually has a meaning. This is the line of node, right? I know this. I know that this is the line of node. So by figuring out what goes in here, I am already able to express the line of node in the ECI basis, which is X, Y, and Z, right? So I already have some useful element. I already have a vector. I already have a direction in space that I'm probably going to use. So what do you want to put in that matrix? Well, I'm going to do the easy one. The Z prime is Z. So how about 0, 0, 1? And then X hat prime projects on X hat as cosine of big omega, and then I have a sine of big omega, and then I have a 0. And for Y, by the way, this is a Y, Y hat prime, well, I have a minus sine of omega, cosine of omega, and then I have a 0. Okay. Now the second rotation does this. Goes from the X hat prime, Y hat prime, Z hat prime. There it is anymore. I rotate about this axis, I, and I go to now Z hat second and Y hat second, and this recycles itself. and this angle is I, and this angle is I. So this is the second rotation. So I have the axis with the second, and we'll continue this next time, but let me do this at least. So now it's going to be just easy to go with this one. That's why we do other angles, because you go step by step with the intermediate axis. You care about one rotation at a time. So how does x prime double dot projects into the prime basis? Well, it's just x prime, so this is 1, 0, 0. How does y hat second projects is, let's see, it's a 0 on the x prime. It's a cosine of the inclination on y hat prime, and it's a sine of the inclination here. And then I should have 0 minus sine of e cosine of e, I, not e, sorry. Can we do the last one? Yeah, I think so. So my last rotation is, I'll put it here. I don't think we need this for now. Is about the z second. Z second is not going to change, so it's going to be equal to z third. And it's a rotation of little omega. And it's going to move my x second and y second into some x third and y third axis. Again, omega and omega. And I'm going to do the same. X, y, z. I'm going to go down here because I don't have any space there. There's a matrix, and there's the basis right before that one, which is the one with the second. And I'm going to figure out how they project. The one that reuses itself is z, so this is again 0, 0, 1. It's going to look like that one, except there is a little omega here. So now I know how each basis projects into the next one, or in the previous one, how every new basis projects into the previous one. So, before we leave, how would you put everything together? How can you go, if you need to, how can you go from the original ECI basis, x, y, and z, to the final one? Well, you multiply all these matrices, right? This matrix, let's call it, it's a rotation about an axis z. So let's call it R3 of big omega. Let's call this one some kind of R1 of I. And let's call this one here R3 of little omega, right? So what do you think you need to put in here? Multiply those matrices. You see that? The ones with the prime are nothing else than R3 of big omega times the basis that is the original one. Here it is. But then if I take the basis with the prime and I multiply times R1 of I get to the basis with the second. And if I take the basis with the second and I pre-multiply times R3 of little omega, I get what I want. I'm not going to write the full-blown product of these three matrices. You can find them in the book. You can do it in MATLAB, symbolic. I don't care. I don't carry that in memory. You just need to remember the key elements. That's why we do other angles, because they're easy single-axis rotations, and then you multiply them together. Now, next time, we're going to try to figure out how to use all these x's, prime, second, and third that we have derived, because they have something to do with these directions. Okay? Start working on converting state vector into orbital elements, if you want, in MATLAB.